In the sterile corridors of the Planck Institute for Astrophysics in Munich, Dr. Sarah Chen stares at a computer screen displaying what should be impossible. The simulation she's been running for 3 months shows the cosmic web in unprecedented detail, that vast network of dark matter filaments connecting every galaxy in the observable universe. But something is terribly wrong with the numbers. According to her calculations, based on observations from the most powerful telescopes ever built, nearly half of all the ordinary matter that should exist in the universe has simply vanished. Not transformed, not hidden behind cosmic dust, but genuinely missing from every census astronomers have attempted. The hydrogen and helium forged in the first minutes after the Big Bang should account for roughly 5% of the universe's total mass energy budget. Yet when she adds up all the matter in stars, gas clouds, and intergalactic space, she can only find about half of what the Big Bang nucleosynthesis models predict should be there. This cosmic accounting mystery forces us to confront one of the most perplexing questions in modern astrophysics. Where did half the universe disappear to? And what does this vanishing act tell us about the true nature of the cosmos we think we understand? To grasp the magnitude of this mystery, we must journey back to the universe's earliest moments, when the very atoms that would one day form stars, planets, and living beings were forged in a cosmic furnace of unimaginable intensity. In the first 20 minutes after the Big Bang, when the entire universe was hotter than the core of the most massive stars, protons and neutrons danced together in nuclear reactions that would determine the chemical composition of the cosmos for all eternity. The physics of this primordial nucleosynthesis is remarkably well understood. As the universe expanded and cooled from billions of degrees to merely millions, the conditions became just right for nuclear fusion on a cosmic scale. Free protons, the nuclei of hydrogen atoms, began combining to form deuterium, then helium-3, and finally helium-4. The process was exquisitely sensitive to the density of ordinary matter in the universe. Too little matter, and the reactions would shut down before significant helium could form. Too much matter, and the process would continue beyond helium, creating heavier elements that we know were actually formed much later in stellar cores. The beautiful precision of these calculations, confirmed by decades of laboratory nuclear physics experiments, tells us exactly how much ordinary matter the universe should contain. The cosmic recipe is surprisingly simple. For every 1,000 hydrogen nuclei created in the Big Bang, there should be about 75 helium nuclei, along with trace amounts of lithium and beryllium. This primordial mixture, unchanged by stellar processing, can still be observed today in the most ancient gas clouds between galaxies. Yet when astronomers began taking careful inventory of the modern universe, they discovered a troubling discrepancy. The stars in galaxies contain only a tiny fraction of the predicted baryonic matter, ordinary protons and neutrons that make up atoms. Even adding in all the gas within galaxies, the diffuse material between stars, and the hot plasma that fills galaxy clusters, the total still falls dramatically short of theoretical expectations. Roughly half of all ordinary matter in the universe has gone missing. The search for this missing matter became one of the great detective stories of modern cosmology. In the 1990s, astronomers suspected it might be hiding in a warm-hot intergalactic medium gas heated to temperatures between 100,000 and 10 million degrees, hot enough to be highly ionized, but not quite hot enough to emit copious X-rays. This gas would be nearly invisible to most telescopes, detectable only through its subtle absorption of ultraviolet light from distant quasars. Dr. Fabrizio Nicastro's groundbreaking work with the Hubble Space Telescope in the early 2000s provided some of the first compelling evidence for this hidden reservoir. By studying the spectra of distant quasars, those brilliant beacons from the early universe, his team could detect the faint fingerprints of oxygen ions in the intergalactic medium. These highly ionized atoms could only exist in gas heated to millions of degrees, precisely the conditions expected for the missing baryonic matter. But finding traces of this warm-hot gas was just the beginning of a much larger puzzle. Computer simulations of cosmic structure formation suggested that this missing matter wasn't simply floating peacefully in intergalactic space. Instead, it was being actively sculpted by some of the most violent processes in the universe: supernova explosions, the formation of supermassive black holes, and the collision of entire galaxy clusters. The story begins in the first billion years after the Big Bang, when the universe was undergoing a phase transition known as reionization. The first stars and galaxies were pumping out intense ultraviolet radiation, stripping electrons from hydrogen atoms throughout the cosmos. This process didn't just change the ionization state of intergalactic gas. It fundamentally altered how matter could flow and accumulate in the universe. Prior to reionization, gas could freely fall into the gravitational wells created by dark matter, forming the first stellar nurseries where primordial stars would ignite. But once the intergalactic medium became ionized and heated, smaller dark matter halos could no longer retain their gas. The thermal pressure of the heated medium overcame the gravitational pull of these mini-halos, ejecting their gas into the vast spaces between developing galaxies. This cosmic feedback process, driven by the collective energy output of the first generation of stars, fundamentally changed the character of galaxy formation. Instead of smoothly accreting gas from their surroundings, galaxies found themselves in competition with thermal pressure that fought against gravitational collapse. Only the most massive dark matter structures could overcome this resistance and continue growing. The European Southern Observatory's very large telescope, perched high in the Atacama Desert, has captured stunning evidence of this ongoing struggle between gravity and thermal pressure. Its observations of the Lyman Alpha forest, a series of absorption lines in quasar spectra created by neutral hydrogen clouds, reveal a cosmic web that is far from static. Gas flows along dark matter filaments at speeds of hundreds of kilometers per second, sometimes falling into galaxies, sometimes being blown outward by stellar winds and supernova explosions. These galactic winds represent one of the most dramatic redistribution mechanisms in the cosmos. When massive stars reach the end of their lives and explode as supernovae, they don't just synthesize heavy elements and scatter them into space. The cumulative effect of multiple supernovae can drive powerful outflows that carry gas completely out of their host galaxies, enriching the intergalactic medium with metals, while simultaneously reducing the raw material available for future star formation. The Spitzer Space Telescope's infrared observations have revealed these outflows in spectacular detail. Galaxies appear surrounded by vast bubbles of hot gas, expanding at velocities that exceed the escape speed needed to leave the galaxy entirely. Some of these bubbles extend for hundreds of thousands of light years beyond the visible galaxy, representing a significant fraction of that galaxy's total baryonic content expelled into intergalactic space. But stellar feedback is only part of the story. At the centers of most galaxies lurk supermassive black holes, and these cosmic monsters play an equally important role in the great baryonic redistribution. When gas falls toward a supermassive black hole, it forms an accretion disk that can become so hot and luminous that the resulting radiation pressure drives powerful outflows. These active galactic nucleus winds can carry away gas at velocities of thousands of kilometers per second, far exceeding the speeds achieved by stellar winds. The Chandra X-ray Observatory has mapped these black hole-driven outflows across cosmic history, revealing that they were most common during the universe's adolescent phase, roughly 8 to 10 billion years ago. This was the era when supermassive black holes were growing most rapidly, fed by the abundant gas reservoirs of young galaxies. The energy released during this feeding frenzy was sufficient to heat and expel enormous quantities of baryonic matter, fundamentally altering the evolution of galaxies throughout the universe. Perhaps even more dramatic are the effects of galaxy cluster formation. When smaller galaxy groups merge to form massive clusters, the gravitational energy released heats the intracluster medium to temperatures of tens of millions of degrees. This process, captured in exquisite detail by computer simulations run on the world's most powerful supercomputers, shows how cosmic collisions can shock heat vast quantities of gas, making it detectable only through X-ray observations. The Planck satellite's all-sky survey of the cosmic microwave background radiation provided an unexpected window into this cluster formation process. through the Sunyaev-Zeldovich effect, where hot electrons in galaxy clusters scatter cosmic microwave background photons and slightly alter their energy. Planck could detect galaxy clusters across the entire observable universe. These observations revealed that the hot gas in clusters represents a significant reservoir of baryonic matter. But even including this component, the cosmic census still comes up short. Recent observations with the EROSITA X-ray telescope have pushed this inventory even further. By conducting the deepest all-sky X-ray survey ever attempted, EROSITA has mapped the distribution of hot gas in unprecedented detail. The resulting images reveal a universe where hot, diffuse plasma fills not just galaxy clusters, but also the filaments connecting them, creating a vast network of heated baryonic matter that extends across hundreds of millions of light years. Yet even these comprehensive surveys cannot account for all the missing baryons. The shortfall suggests that significant quantities of ordinary matter exist in a phase that remains largely invisible to current observational techniques. Some of this matter may be in the form of extremely hot gas, heated to such high temperatures that it emits primarily in gamma rays rather than X-rays. Other components may exist as cold, molecular gas in the voids between galaxies, too diffuse and cool to be easily detected. The search for these hidden baryons has led to increasingly sophisticated observational strategies. Fast radio bursts, the mysterious millisecond duration pulses of radio emission from unknown sources, have emerged as an unexpected probe of intergalactic matter. As these radio waves travel across cosmic distances, they interact with free electrons in their path, causing different frequencies to arrive at Earth at slightly different times. This dispersion effect provides a direct measure of the total electron content along the line of sight, offering a new way to census the missing baryons. The Australian Square Kilometre Array Pathfinder has detected dozens of these fast radio bursts, and preliminary analyses suggest they may indeed be revealing significant reservoirs of previously undetected ionized gas in intergalactic space. If confirmed, these observations could finally solve the missing baryon problem, showing that the lost matter has been hiding in plain sight as a warm, ionized medium that fills the vast spaces between galaxies. But the implications of the missing baryon mystery extend far beyond simple cosmic bookkeeping. The distribution of ordinary matter in the universe plays a crucial role in structure formation, galaxy evolution, and even the conditions necessary for life. If half of all baryonic matter has been expelled from galaxies and heated to extreme temperatures, this fundamentally changes our understanding of how cosmic structures grew and evolved over billions of years. Computer simulations that include these feedback processes paint a picture of a universe where galaxy formation is a far more violent and chaotic process than previously imagined. Instead of smoothly accreting matter from their surroundings, galaxies undergo cycles of growth and mass loss, sometimes ejecting more material than they retain. The largest galaxies, those massive ellipticals that dominate galaxy clusters, appear to have shut down their star formation almost entirely through these feedback processes, transforming from active stellar nurseries into cosmic graveyards filled with aging red giants. The Hubble Space Telescope's deep field observations provide striking visual evidence of this transformation. Distant galaxies, seen as they were billions of years ago, appear blue and actively star-forming, with irregular morphologies suggesting ongoing mergers and interactions. Nearby galaxies, representing the modern era, are predominantly red and elliptical, their star formation quenched by the accumulated effects of stellar and black hole feedback. This cosmic transformation has profound implications for the future of the universe. If feedback processes have already ejected half of all baryonic matter from galaxies, the raw materials for future star formation are becoming increasingly scarce. The universe may be entering an era of cosmic recycling, where new stars can only form from material that has been previously expelled and is now cooling and falling back into galaxies. The James Webb Space Telescope's unprecedented infrared capabilities are beginning to reveal this recycling process in action. Its observations of distant galaxies show complex networks of gas flows, with materials simultaneously falling into galaxies along dark matter filaments while being expelled by stellar winds and black hole outflows. These competing processes create a delicate balance that determines whether a galaxy will continue forming stars or enter a phase of quiescence. But perhaps the most intriguing aspect of the missing baryon problem is what it reveals about the interconnectedness of cosmic processes. The matter that was expelled from galaxies billions of years ago didn't simply disappear. It became part of the intergalactic medium, where it continues to influence the formation and evolution of new structures. This expelled material carries with it the chemical signatures of stellar nucleosynthesis, enriching the intergalactic medium with heavy elements that will eventually be incorporated into future generations of stars and planets. The Atacama Large Millimeter Array has detected this chemical enrichment in action, observing carbon and oxygen absorption lines in gas clouds that lie millions of light-years from the nearest galaxy. These observations provide direct evidence that stellar feedback has not only redistributed baryonic matter, but has also spread the products of stellar nucleosynthesis throughout the cosmos, creating a truly universal chemical evolution. As we piece together this cosmic puzzle, we're beginning to understand that the missing baryons aren't really missing at all. They've simply been transformed and redistributed by the most energetic processes in the universe. Like players in a cosmic shell game, these atoms have been shuffled between different phases and locations, making them difficult to detect with any single observational technique. The resolution of the missing baryon problem is forcing astronomers to develop new theoretical frameworks for understanding galaxy formation and evolution. Instead of viewing galaxies as isolated island universes, we're beginning to see them as nodes in a vast cosmic ecosystem, constantly exchanging matter and energy with their surroundings. This perspective highlights the importance of feedback processes in regulating cosmic evolution, and suggests that the universe's current structure is the result of a delicate balance between gravitational collapse and energetic outflows. Looking toward the future, next-generation observatories like the extremely large telescopes being constructed in Chile and Hawaii promise to finally complete the cosmic census of baryonic matter. These instruments will be capable of detecting even fainter absorption lines in quasar spectra, mapping the warm-hot intergalactic medium in unprecedented detail, and potentially revealing the last hiding places of the universe's missing atoms. The Square Kilometer Array, when completed, will provide another powerful tool for this investigation. Its unprecedented sensitivity to radio emission will allow astronomers to detect hydrogen gas throughout the cosmic web, potentially revealing cold baryonic reservoirs that have remained invisible to optical and X-ray telescopes. Combined with continued observations of fast radio bursts, these facilities may finally solve the 3-decade-old mystery of the missing baryons. But beyond simply accounting for all the universe's ordinary matter, resolving this mystery will provide crucial insights into the fundamental processes that shaped cosmic evolution. Understanding how and when baryonic matter was redistributed throughout the universe will help us better predict the future of galaxy formation, the potential for life in different cosmic environments, and the ultimate fate of structure in an expanding cosmos. The story of the missing baryons reminds us that the universe is far more dynamic and interconnected than it might appear from our earthbound perspective. The atoms in our bodies have likely traveled vast distances through intergalactic space, perhaps spending eons in hot galaxy cluster gas, before eventually condensing into the molecular clouds that formed our solar system. We are not just made of star stuff, as Carl Sagan famously observed, but of matter that has participated in the grandest recycling program in the cosmos. As Dr. Chen continues her analysis in Munich, refining her simulations and comparing them with the latest observational data, she's participating in one of science's most ambitious projects, creating a complete inventory of everything that exists in the universe. The missing baryons represent more than just a cosmic accounting problem. They're a window into the complex feedback processes that regulate cosmic evolution, and a reminder that even our most basic assumptions about the universe can hide profound mysteries. In the end, the great cosmic vanishing act may teach us that in a universe governed by violent stellar explosions, powerful black hole winds, and titanic galaxy collisions. Nothing stays in one place for long. The missing half of ordinary matter hasn't disappeared. It's simply been caught up in the universe's grandest magic trick, transformed and redistributed by processes so energetic that they can move matter across millions of light years and heat it to temperatures found nowhere else in nature. The resolution of this mystery will mark another milestone in humanity's quest to understand the cosmos, but it will also open new questions about the role of feedback in cosmic evolution and the ultimate destiny of matter in an ever-expanding universe. In our brief moment of consciousness, we have the privilege of witnessing this cosmic shell game and perhaps, for the first time in universal history, figuring out where all the missing pieces have been hiding.